Okay, we're going to talk about bonding theories. I want to go over a couple of bonding theories that you've probably been exposed to some of them, but maybe not all of them. So what we're going to be discussing is on the elementary level, why do elements bond, of course, and then what are those bonds made of? And I want to talk with you specifically about ionic bonding, valence bond theory, molecular orbital theory, and then coordinate covalent bonds. So why would an element bond? Well, there's a couple of reasons why it would bond. Um, Basically, because they want to achieve the lowest energy interaction. And so if you look at this kind of a system where you have hydrogen nuclei that are far apart from each other or closer to each other or in an ideal bonding situation, right? What happens here is you have reached the ideal distance where the attractions of the electrons for the nuclei are maximized and the repulsions of the electrons from each other and the nuclei from each other are minimized. And that's what this distance, the bond length for hydrogen is. Of course, hydrogen is not going to be staying at 74 constantly because, electrons are moving all the time. And so this is going to shift back and forth here, of course. But according to Coulomb's law, right, opposite charges attract, like charges repel, the forces are stronger the closer you are. And so what bonding does is it maximizes the attractive forces and minimizes the repulsive forces. And so the bonds are made of electrons, right? So they must be made of electron pairs. But because electron pairs are waves, they're wave-like, it makes it difficult to understand exactly how they work. So we have a couple theories that we've developed to try to simplify this in some way. So let's go with the easiest ones. Those are ionic bonds, right? They are electrostatic attractions of oppositely charged particles. And if I switch to presenter mode for a second, I can draw on this for you. And then you can see that these are repulsions, right? They're trying to get away from each other. These are repulsions. They're trying to get away from each other, right? But then you have attractions between positive and negative charges, right? And there's lots of attractions, right? And they're trying to maximize those attractions and minimize the repulsions. And so that's what ionic bonds are, right? Is just the oppositely charged particles nestled close to each other, held together by Coulombic attraction. And so this is going to be annoying. Okay. So if we go for valence bond theory is for covalent molecules, right? So ionic bonds are great for metal-nonmetal interactions, but what happens when you have two nonmetals or a nonmetal and a metalloid or some sort of combination of metals, nonmetals, and other nonmetals? Well, then you have valence bond theory. Valence bond theory is considers the electrons localized, meaning that the electrons for this hydrogen atom are localized to this hydrogen atom. This hydrogen atom is localized together, and then when you bring them together, those orbitals overlap. And where there is an overlap, then there's a bond, right? And so this is called a sigma bond. Sigma bonds are indicated because they lie along the internuclear axis. There's electron density along the internuclear axis between the nuclei. And then you can also have pi bonds form. Pi bonds are forming when you have an overlap of p orbitals. And so this is the nucleus here and the nucleus here for the two atoms, right? But notice the overlap is above and below. And so when you have that overlap above and the overlap below, that is a pi bond because there is a node where there's no electron density on the internuclear axis, and that's what makes it a pi bond. Okay, so these overlaps can come from s, p, and d orbitals, or they can come from hybrid orbitals. So if you're like a methane molecule, right, a CH4, then you can look like this, right? You're bonded to a hydrogen up here. Sorry, hydrogen over here, hydrogen down here, right? And you draw these bonds, and this is valence bond theory, right? It says these are the bonds, right? Connecting the carbon to the hydrogen. And the way that the carbon is able to do this is because it makes 4 bonds by taking the 4 atomic orbitals and making 4 hybrid orbitals out of it. And so each of these is a hybrid sp3 orbital, right? sp3 hybrid. Whereas the hydrogen is just their s orbital that's overlapping with the sp3, making these sigma bonds, right? And you can form pi bonds if you had to make like ethane or ethene, sorry. Then you would have a double bond, and that would be a sigma bond and a pi bond, right? Valence bond theory requires multiple structures to describe resonance, however, because once you determine where a double bond is, right, that double bond is defined in space, right, and then you have to write it again in another type of structure if you wanted to show that there's more than one possibility for that double bond. But it also helps to predict molecular shape, right? You can have this kind of a shape. If you had like a hydrogen bonding to a hydrogen, that would be linear. But if you have 4 orbitals around your carbon, then that would be tetrahedral, right? And so this works for linear, trigonal, planar, tetrahedral, so on and so forth. Valence bond theory describes that very well. So it's very simple. You draw lines, and that represents bonds, and everything's good, right? But unfortunately, because it's very simple, it can be very misleading. So we have molecular orbital theory. It's a little more complicated. What this does is it considers electrons as delocalized throughout the entire molecule. So they're not necessarily shared between atoms. The electrons are delocalized. And then you have atomic orbitals combining to form molecular orbitals. So in this case, you have a hydrogen, right? And the 1s from this hydrogen and the 1s from this hydrogen are combining together. And when they combine together, you have the options. It's going to form 2 molecular orbitals. So 2 atomic orbitals equal 2 molecular orbitals. And then you have a sigma and then a sigma star. You have the bonding orbital and then you have the anti-bonding orbital. This is because your s can add to your s, and then you get the bonding orbital, or your s orbital can subtract from the other s orbital, and then you get the anti-bonding orbital. Notice that there's no electron density in between the nuclei on the anti-bonding orbital, and that's what makes it anti-bonding, right? And so you can calculate bond order in this way. If you add up all the bonds and subtract the number of anti-bond orbitals that are filled, then you can figure out the bond order for the atoms. And for the most part, this matches up quite nicely with valence bond theory. But there are a couple of instances where it doesn't match up. But it helps in those instances to more accurately reflect reality, right? And so instead of just having pi bonds, then if you combine your p orbitals with molecular orbital theory, then you can get pi and pi star. You get pi bonding or pi anti-bonding. If you take p plus a p, you get pi bonding, and then the p minus a p, you get pi anti-bonding. And so what happens here, I'm going to end this for a second, go back. you get these different orientations for your diatomic elements. It's very easy to do molecular orbital theory with diatomics. When you're doing it with more than just two elements, it becomes quite complicated quite quickly. And so we're not going to do that, but I just wanted to show this to you. Because if you fill in the electrons in these guys, you can see that theoretically lithium, dilithium, would be something that could exist, right? Because it has two electrons in the 2s anyway. And so you put one here, you have a pair of electrons in the sigma orbital. That would be one bond, and so the bond order for lithium would be 1, and life is good, right? And for dilithium. And so dilithium could exist, which explains why Gene Roddenberry used it for Star Trek, right, as a power source. But diberyllium would not be able to exist because you have 4 electrons. You have 2 electrons in the 2s, and then 2 electrons, or sigma 2s, 2 electrons in the sigma star 2s. And so it wouldn't be able to exist because the bond order would be 1 minus 1, which is 0, right? Molecular orbital theory helps to predict some other cool things. Like if you go down to oxygen and you put electrons in oxygen, you would see that when you get up here to the sigma star or the pi star, there's 1 electron here and 1 electron here. And that shows oxygen having unpaired electrons, meaning that it would be paramagnetic. And when you subject oxygen to a magnetic field, it does interact with that magnetic field, meaning that it is paramagnetic. So this helps to explain that observed phenomenon. Also, this helps to determine whether something is an insulator, a semiconductor, or a conductor based upon the distance of this band gap, this HOMO-LUMO band gap. And so in the atomic orbitals screencast, I talked about band gap and HOMO-LUMO theory to some extent. But this allows you to see where specifically those highest occupied molecular orbital and lowest unoccupied molecular orbital would be in molecular orbital theory. So it would be in an anti-bonding or in the next bonding orbital, right, for your higher energy level. And so when that band gap gets really small, like these band gaps right here or this band gap right here, right, then they become conductors. And so when you have multiple pi bonding orbitals that are next to each other, it lowers their band gap and you get more conductance in those molecules. And so this is kind of the theory behind organic semiconductors, right? Because you can make pi conjugated systems or double bond systems that are repeating, and those double bond systems that are repeating have a lower band gap, lower energy gap for those the electrons to jump in order to be able to conduct electricity. So the last one that we're talking about is coordinate bonds. Coordinate bonds are actually a type of secondary bond, like dipole-dipole bonds and hydrogen bonds, that they're not actually bonds, but they kind of are because there is an orbital overlap. Okay, so in coordinate bonds, you have one species that donates the electron pair and the other species that donates an empty orbital. So in this case, we have the ammonium ion, right, being formed from an ammonia that has a pair of electrons, right, that's in an orbital that's filled, and you have hydrogen ion that has empty orbital. It has the empty s orbital, right? And so that empty s orbital just overlaps with the space that this electron pair occupies, and you get a bond formed. It's a coordinate bond. This was the most easy way to illustrate it with ammonium, but the most common way that we're going to talk about it is with metals.
and they're d orbitals, providing the electron space or providing the empty orbitals. And so that's going to allow for some really cool chemistry to happen.